So the next speaker is John Rakovan. I've known John for a long time, and he's one of the few crystallographers who seems to talk in English, as near as I can tell. So the challenge with finding science speakers for these symposia who could talk, who could talk English to us and explain the science, is to also find one who understands what we want to see and learn about, which is to know more about these beautiful things that we already love. And since John is a collector too, and one of your peers is a collector, he's the perfect guy to talk about this. He is generally thought of as the go-to guy for those what the hell is this kind of questions when you have a mineral or a crystal you can't figure out what it is. You know what it might be, but something's puzzling about it. So people go to John. And I guess my version of the subtitle of his talk would be, how lucky we are that nature gives us this amazing, beautiful art, and we're going to learn a little bit about how it actually forms. John?
Great. Thank you, Rob.
How about it?
All right, as Rob said, one of the things that I think is most intriguing to us as collectors and me as a scientist and others as scientists is you show somebody a pyrite from Logroño, Spain, and if they're uninitiated to mineral collecting, they can't believe that Mother Nature did that. How did this form? They think that it's something that's been polished in a laboratory or by a lapidary. And so the beauty of the symmetry of crystals and the fact, just the plain fact that they come out of the ground with flat surfaces as if they've been polished. How does Mother Nature do this? And that's the topic of this talk. The question is, how do crystals form? This is a crystal of apatite. You might recognize the hexagonal shape here. This particular crystal is about 2.5 centimeters across. There's a scale bar, it's 5 millimeters. Even the smallest crystals can have faceted shapes to them, the regular morphology that we see. And as an example, here's another apatite crystal, same shape, the hexagonal outline that we see here, we see on this apatite. But in this case, our scale bar is 5 nanometers. We're actually seeing this crystal at the atomic scale, and I'll explain in just a moment how this is done. But you can see the lattice of atomic planes within the structure. Yet even at this size, we have that regular crystal shape. How does that happen in nature? All right, so let's break the question down further into several other questions, and that is, for example, why are crystals bound by flat faces in the first place? We take a beautiful example, the sceptered amethyst from Hopkinton, Rhode Island. We see the nice flat surfaces. Why do those form in nature? Most things don't have that kind of flat, polished surface or geometric shape. Another aspect is, if we compare these two garnets, this one is bound by the trapezohedral surface, this one is bound by the dodecahedral surface. Why do crystals form different shapes? For those of you who are calcite crystals or calcite crystal collectors, you know that there are literally thousands of different shapes and forms that we see in nature. What controls those differences? Why do we have those? And then finally, given a set of crystal faces, for example, these are two apatite crystals, this one bound by the prism and pinacoid, same with this with some pyramidal faces. Why does this one elongate and this one tabular? What controls the morphology of the crystal if we have a certain set of crystal faces? And so to try to address the question, how do beautiful crystals form? Let's look at these specific questions as we go through this. So here's our apatite crystal again. Again, that beautiful hexagonal morphology or symmetry that we can see here. Also at the atomic scale, we can see that same morphology. And in this case, we can see the planes or lattice of the atomic structure. And I'm going to show you an overlay here. There's the outline of the lattice describing those atomic planes. And I want to use a bit of terminology here, so I'm going to superimpose on this some red dots where all of those lattice planes cross. And we'll call those lattice points or lattice nodes. Early researchers, early scientists who were trying to answer the question, well, why are these crystal faces common in nature and others are not? They came to the conclusion that, here's our lattice again, that we saw in the previous example. They found that planes that are common on crystals, and here are the hexagonal planes of our apatite crystal, those are commonly found if they have a high density of lattice points on them. If they have a low density of lattice points, here's another example. You can see there's a high density of lattice points on this plane, but this plane, much lower density. The observation was that the frequency with which a given phase is observed on a crystal is proportional to the density of lattice points along the plane. So those crystal faces that had a lot of lattice points on them were commonly seen in nature, and those that did not, for example, this one here, were much less common. And these were described by Bravais and Donnet and Harker, and they were known as the Bravais and Donnet and Harker laws. They're purely empirical. They were simply based on observation, and they hold today, but ultimately they don't answer the question why. They just tell us, well, this is a correlation that we happen to see. In the end, we've found, particularly in the last 50 years, in terms of studying crystal growth in the laboratory and then comparing that to what we see in nature, we've found that the ultimate reason for this, and it makes sense from a standpoint, we're all used to these types of things, whatever is the lowest energy of a system, and a crystal growing in a pocket can be considered a system, whatever is the lowest energy, that's going to be the favored configuration. And so what we know today is what controls which faces will grow onto a crystal is essentially the interfacial energy between the crystal and its environment. So Joe showed all of these pockets of feldspar and quartz crystals where those grew from a solution in that pocket. The morphology of those crystals is based on lowering that interfacial energy between the feldspar and the quartz and the fluid from which they are growing. It turns out that there are a lot of different factors which will affect that interfacial energy, and so those ultimately are the controls that allow variation from one pocket to another or from one deposit to another. And these include temperature, pressure, fluid chemistry, and the chemistry of the crystal as it's growing, the growth rate, the presence of defects. I'm going to talk about some of these things like dislocations. There are many factors that we do know ultimately control that interfacial energy, and hence these are the factors that control which crystal faces will form. As an example in terms of fluid chemistry, and I want to point this one out because we see it in the field very often, but it's also well recognized in the laboratory. And actually the mechanism by which this occurs has been determined experimentally. I'm not going to get into it, but I'm going to show you a beautiful correlation between chemistry and morphology. For example, if you grow calcium carbonate from a solution with dissolved calcium and carbonate ions in solution, and you do that in a pure solution at room temperature, the morphology of your crystals is dominantly going to be a rhombohedral crystal. For example, this is a rhombohedral crystal from Sumeb, Namibia. This is the morphology that you would get if you do that experiment. However, in your solution, if you add a little bit of magnesium and allow the crystal to continue to grow, that magnesium will cause a complete change in the morphology, and you'll get scalenihedron, typical of the types of calcites you see at Elmwood, Tennessee. And this is exactly what we see in the laboratory. So the addition of a little bit of an impurity in solution completely changes the morphology. Now, take into account the possible temperature range, pressure range, all of the elements that could potentially be in that solution from the periodic table, and you have a myriad of different possible combinations and hence different forms or morphologies that you're going to see in calcite. We have yet to work these out. If we can understand what all of those controls are, you can take a crystal like this and then say, this must have been the set of conditions in this geologic environment. It's telling us something. We just don't know what it's telling us yet. It's a very complex interplay of many, many factors, but this is ultimately what causes the variations that we see in our mineral specimens. All right. Morphologic perfection in our specimens and internal perfection, if we have gemmy specimens or we're interested in gem crystals, we want to have few defects, transparency, color, etc. These are both favored when crystal growth occurs unrestricted. For example, here's a pegmatite pocket. This one not from Colorado, but from the Naegi Pegmatite District in Japan. And the granite surrounding the pocket is comprised of feldspar, microcline, and quartz and mica. Those feldspar crystals are anhedral. They're all grown into one another. They don't have a regular shape because they've come into contact with one another. However, when the feldspar can grow into the open pocket, we form a nice euhedral or subhedral crystal, such as this one here. So unrestricted environment is very important, and that's why when we're out mineral hunting, we're always looking for the pockets. That's where we're going to find our best crystals. Slow crystal growth. I'm going to draw the analogy of growing a crystal to building a brick wall. If you bring your bricks up and align them neatly and put your mortar in there, you're eventually going to get a nice smooth brick wall. But if you do it very hurriedly and you're not precise with where you put your bricks, you're going to end up with a rough surface. Slow crystal growth promotes perfection in terms of morphology. And this is controlled by a number of things, including a homogeneous and stable environment. And Joe mentioned the fact that during the formation of a pegmatite pocket like this one, oftentimes it is not a stable environment, and as it evolves, you can actually get physical rupture due to the hydrostatic pressure in the pocket, or the fluid pressure in the pocket. That's very unstable and leads to rupture and also damaging of the crystals. Okay. So crystal growth can actually occur in many different types of media, and we're familiar with many of these. The granite that I just showed you, those crystals solidified from a melt. That is, we had a rock that was molten. In nature, these are examples of this are lavas or magmas, and as they solidify, we can grow crystals. Most of the specimens, however, that we have in our collections are crystals that actually have grown from solution, and this is what we're going to focus on today. Solution growth in nature, most of what we have is dominantly a solution comprised of water and dissolved solutes, and these are examples such as hydrothermal fluids or even groundwaters. There are other types of natural solutions, carbonate solutions and others, but we're mostly going to be looking at aqueous solutions. We can have crystal growth from a gas. For example, many of you may have seen photographs of sulfur crystals forming along the sides of rocks where gases are evolving from a volcano. These are volcanic fumaroles. I'm going to show you a really interesting example of a specimen from a fumarole from Ohio. It has nothing to do with volcanoes, very interesting environment, but it's growing, these crystals are actually growing from a gas. And then finally, we can also have crystal growth from a solid. This is common in metamorphic environments where one mineral under different pressure temperature conditions will change to another, and the crystal is actually growing in the solid state. But again, most of the specimens we're interested in are the result of crystal growth from solution, so this is what we're going to focus on. And it turns out this is, from a scientific standpoint, because we can reproduce this most easily in the laboratory on timescales that we can monitor, this is the area of crystal growth where most of our understanding comes from. Okay, since we're dealing with solutions that use a little bit of terminology, here I have 3 solutions. Assume that these are solutions of water, so the solvent is water, and what we have are ions or solutes dissolved in the water, say sodium chloride. If the water has fewer dissolved ions than it can hold, we say that it is or undersaturated. When we reach the point where the water has just the maximum amount of water that it can hold in a stable configuration, what we call equilibrium, this is saturated. However, it is very common that we can supersaturate a solution. That is, we can put more dissolved ions into solution than it wants to hold. We can do it, so it does exist. But the solution wants to change. And how does it want to change? It wants to get rid of some of these ions that are dissolved. How does it do it? By crystallization. The precipitation of a mineral now removes some of those ions, and that's the driving force behind crystallization from solution. When these become supersaturated, minerals want to precipitate to drive it back to the state of saturated solution. Okay, so precipitation is the process by which we're forming crystals. So we're going to look at this, and we can break it down into 2 regimes. The first is the nucleation, where our crystals just start to form. Essentially, we have a very small number of atoms in the nucleation stage, and then eventually when our crystal becomes large enough, we say that the continuous addition of atoms is crystal growth. And this is semantics, but we're actually going to describe this in terms of what's going on in solution. So here we've got a supersaturated solution, our dissolved ions. We want to decrease the number of ions in solution, and we can do that by crystallization. If the nucleus of our first crystal forms freely in the solution, that is not bound to the walls of our pocket or on top of another crystal, for example, the goethite that Joe showed, those goethites nucleated on the quartz crystal. If our crystal actually nucleates freely in solution, we call this type of nucleation and growth homogeneous. I'm going to show you a video here of the homogeneous growth of some crystals from solution. So this is a droplet that is supersaturated. Well, actually, it's saturated with respect to some solutes. And the video that I'm going to show you was taken over a 3-day period of time. So this is a time-lapse video. The supersaturation of this droplet was done by cooling. So who here has ever made sugar candy? Okay? Or sugar crystals. What you do is you heat up the water on the stove, you dissolve your sugar because you can put more sugar into hot water than you can into cold water, and then as you cool the water, it becomes supersaturated and the sugar crystals come out. And the same thing is occurring in this droplet. It's being done on a microscope stage, however. And what you'll notice is homogeneous nucleation and crystal growth, because the crystals that are forming here, you can start to see them grow, and they're growing outwards. They're forming homogeneously. They're floating freely into solution. What you can't see because of the scale is the growth of this is taking place as atoms, the solutes dissolved in this solution, are attaching to the surface, and the crystal grows outwards. Now, look at how the crystals want to grow. They want to grow freely into solution with bound crystal faces. It turns out that this sort of morphology is the energetically most favorable way for a crystal to grow, and that's why they commonly do that. So the question is, how does a crystal actually grow so that the faces are flat? How is that possible? Again, think about the faces on that perfect pyrite cube from Spain. Even the advanced collector, something I love every time I look at it or I teach mineralogy class, and I get to pull out the specimen of pyrite, it's a marvel that that can form in nature. How does that happen? Let's take a look at that. Okay. If our specimens, however, if we look at most of the specimens that Joe presented, crystals are growing on top of one another. So we had the smoky quartz and the feldspar, which grew out of the granite, and the goethite grew on top of that, or the fluorite grew on top of that. We usually don't have freely floating crystals forming in solution, what we as collectors would call floaters. That's atypical. Usually our specimens are matrix specimens. And the reason for that is that if our solution becomes supersaturated, it actually doesn't have to be as highly supersaturated to form a nucleus on a pre-existing surface. When this occurs, this is known as heterogeneous nucleation, and it's favored energetically, and so most of our specimens, most of the crystals that we're going to see are growing on some other crystals or some substrate, such as this apatite growing on the mica. The apatite nucleated on the mica and then grew out into a pocket. The mica itself, you can't see it, but is attached to a granite surface on the back. So it heterogeneously nucleated and grew on the granite surface. And that's how most crystals are found. Now, this is only one of 2 slides that's going to get really technical, and hopefully you can follow me here. But the take-home point is that the position of the top of these curves is different. And let me explain what this represents. Imagine that we have a crystal or a nucleus forming in solution. This is our nucleus or our crystal, and as the size of the crystal increases, so does its radius. On this axis, we have the crystal size, increasing from left to right. On this axis, we have energy, and right at this point where they cross, we're at 0 energy. Now, as I mentioned before, everything wants to move to a low energy situation, and so if our solution is supersaturated, it wants to crystallize. It wants our crystals to grow so the saturation state can move towards equilibrium, and that's going on out here. As crystals grow, you'll notice that these curves become more and more negative. They move in this direction, and that's what wants to happen. But before we get there, we have to overcome these energy barriers. There are barriers to forming that crystal when our size is out in here. And this is how we actually define the stage of nucleation. It has to do with the energetics. Homogeneous nucleation, remember that's the free-floating nucleus and growth into solution, what we saw in that video. The energy barrier to that is shown by the blue line here. It's fairly high. However, if that nucleus forms on a pre-existing substrate, the goethite forming on a quartz crystal, the energy barrier is much lower. It's favored, and that's why most of our crystals are forming on matrices. An interesting phenomenon is if the crystal that's growing on a substrate, if the goethite growing on quartz has a similar atomic arrangement or the spacing between atoms is similar, instead of just getting heterogeneous nucleation, we get oriented heterogeneous nucleation, meaning the crystal that's growing specifically orients itself relative to the structure of the mineral that it's growing on top of, and this is something we all know as epitaxy. the beautiful examples of rutile growing on hematite, notice the orientation is not random. It's forming a hexagonal pattern where the rutile is growing in only one of 3 directions. And the reason for that is the crystal structures of the 2 minerals are meshing, and we can even lower the nucleation barrier further if the crystals grow in an oriented fashion. So that's why we get the beautiful examples of epitaxy that we see in minerals. All right. So that's a little bit about how crystals start to grow and the different aspects of nucleation, why crystals form on matrices, why we have epitaxy. The ultimate question that we're interested in answering here today, however, is this, and I hope that this talk gives you a little impetus to look at your mineral specimens differently. If you're not used to doing this, instead of just looking at them with the light so that you can see the colors beautifully, hold them in the light until you get specular reflection. And that's what I'm showing in this slide here. This is a quartz crystal with very flat surfaces. It's a clear Herkimer diamond. But if I get the light just right, I get full reflectance of that light off the surface. And as I rotate that ever so slightly in the specular reflection, what you'll start to see is topography on the surface. Even though it looks like it's a beautifully polished, absolutely flat surface, that doesn't exist in nature, actually. All surfaces have microtopography, no matter how beautifully flat they actually look. And oftentimes you can see this on a hand specimen if you get the specular reflection. This is a pyrite crystal from Mexico. And if you were to look at it in another orientation, it would look just like those from Spain. You wouldn't see any texture on it. It's absolutely flat. But in this case, I'm getting the light hitting the surface just at the right angle, and we can see these beautiful patterns, the step orientations and the changes in those. This topography, or microtopography, is created during the growth process of the crystal and actually can tell us something about how this crystal formed. So what we're going to do is start to look at microtopography on surfaces and try to understand what this tells us about the formation of nice flat crystal faces. Carl Francis, who's a good friend and actually somewhat of a mentor. I've known him since I was a young kid, and he's the one who finally got me, and I know many of you in the audience, to specialize in your collecting. He now has become a young kid at heart and is collecting a variety of different things, but one of his interests is looking at growth phenomenon, and he has a collection of samples that show things like steps, like this pyrite sample. Okay, so let's start off with some schematics, and then I'm going to show you some real surfaces at a very, very small level. Imagine that we're growing a crystal, so we've got a nice flat surface, and that is this drawing here. How does the crystal grow from solution? We just saw the crystals expanding, but what's happening on the atomic scale? Well, atoms out in solution are coming down to the surface by either diffusion or advection. They have to attach to the surface. And by bringing your bricks to the wall and attaching them to the wall, that's how a crystal grows. But it's actually a much more dynamic process. And I'm not going to show that here because it would be far too complicated to watch. But atoms are moving, attaching, diffusing around on the surface, forming bonds, detaching. And there's a lot of this going on. So atoms are attaching and detaching. If more atoms are attaching than detaching, given a certain period of time, we have crystal growth. If more are detaching, we have dissolution. And at equilibrium, it's actually a very dynamic situation. If we're in solution, things are coming off and going down, but the overall flux is zero. Basically, we don't have any net addition or subtraction from the surface. So let's watch what happens with crystal growth. Our atoms have to diffuse to the surface and attach. And before this atom detaches and goes back into solution, other atoms have to come down and attach to it. And incorporation, for that atom to actually become part of the bulk crystal, not by diffusion, that's actually very unfavorable, it has to get buried. So incorporation is essentially due to burial. Other atoms have to come down and attach to it. And before that detaches, another atom has to come down. And so this process continues until we reach some critical point. And this is similar to a heterogeneous nucleus. Just as we saw with the nucleation, in this case, the nucleus is the same mineral as what we're growing on top of. So you can think of each layer of atoms that's added to a crystal is going through this process of re-heterogeneous nucleation. And once we reach this critical size, then that two-dimensional nucleus will spread out, atoms will attach to this step, and this will move in this direction. likewise in all directions, and we will add a flat layer to the surface. Now, in reality, that doesn't happen just that way, but that's the general idea. And this process, the addition of layers of atoms, layer by layer, in this nice, neat fashion, is known as two-dimensional nucleation and spread, and it's one of the mechanisms by which we form nice, flat crystal faces. Now, in reality, surfaces probably look like this as they're growing. That is, we form many two-dimensional nuclei. This one over here has no idea what's going on over here, but there's attachment and detachment taking place in both areas. And as these become stable, they will spread out, and then all of these islands will coalesce, forming a layer, and then another layer will form, et cetera. So this process, again, is known as two-dimensional nucleation and spread. To do this, however, every time we add a new layer or a new two-dimensional nucleus, we have to overcome that energy barrier. Remember that blue line or the red line in my diagram? That takes some effort to do that. That was a schematic. Now I'm going to actually show you real mineral surfaces on the scale that I was trying to represent there, on the atomic scale. And to do that, we use a tool called atomic force microscopy, and another one that's related, scanning tunneling microscopy. And these are just amazing techniques where we can actually see the microtopography on the atomic scale. I'm going to show you images of atoms, real pictures of atoms, and atoms moving as crystals are growing. And essentially, the idea of how an atomic force microscope works is we have a sharp stylus, like a phonograph needle, riding over a record. And as it rides over the record, we keep track of the height of that. Using the technology of the technique, we have sub-angstrom resolution. That is, we can see differences in both vertical and lateral position of our tip with resolutions better than the diameter of an atom. So sub-angstrom resolution, and that's the only way in which we could see atoms using a technique like this. So the actual surfaces that I'm going to show you now are taken by atomic force microscopy. Here's one of them. Joe, this is a goethite crystal from, I believe, one of your finds in Colorado. Now, this is on a much smaller scale. We'll look at the scale laterally here are 8 by 8 microns. And this is the cleavage surface. You can see the topography here. I've taken one of the goethites. In fact, I think the goethites from Colorado are probably the largest on Earth. Some of them get very large, and so they're really useful from an experimental standpoint. And actually, my postdoc was looking at the surface of goethites from Colorado. And this is from that work, and what we see here is topography now on a scale that we could never see with the naked eye. Only the AFM can see this, but we'll see examples of this on a larger scale as well. So 8 by 8 microns, what we notice is that we have areas in here, these are truly atomically flat. If we could see the atoms, these would all be in the same plane, and we'll call that a terrace. You can see that this terrace is separated from another terrace here by a step. So we basically have a staircase of steps separating these terraces. The height of these steps is roughly 10 angstroms. It is a single unit cell of the goethite structure. And in fact, in some cases, we can see steps that are single atomic layers high. And I'm going to show you one of those in just a moment. So this is what the topography of a natural crystal surface, this one being a cleaved surface, might look like. And we find all different types of patterns on here, just like we saw on that pyrite crystal. Now, here's a schematic showing that same surface. I want to talk about this in the context of adding atoms. We typically don't have a truly flat surface that atoms come down and attach to. Atoms in solution, and in our schematic here, let's say our atoms are these square cubes. And they come down and they see the topography that we just saw on that goethite surface. So we have terraces, we have steps. Some steps are not straight. They actually have bends in them. We'll call those kinks. Now, from an energetic standpoint, this atom has to come down, attach, and get buried before it detaches if it's going to become incorporated. So let me ask you some questions. Imagine that every time one portion of the atom surface is in contact with the surface of our crystal, we're going to form a chemical bond. If our atom comes down and attaches to the terrace site, how many chemical bonds do we form? 1. If it either diffuses to or attaches directly to a step site, how many contacts or bonds do we have? 2 in the step site. If it's in a kink site, how many bonds are 3? Okay. Now remember, there's a probability that these atoms are going to detach, go back into solution, and then it can't get buried. The atoms that are most strongly held with the greatest number of bonds will have the greatest probability of eventually getting buried and becoming incorporated. And in fact, this is what we find, that most of the incorporation takes place along steps and specifically at kink sites within the steps. And most atoms that attach to terraces go off into solution and then eventually come down, and if they're going to become incorporated, it'll happen along these structures here. All right. So our step actually grows outwards in this direction by the addition of atoms at kinks. So it'll translate in this direction until it hits the edge. We start a new kink, it translates, and by doing that, the step is moving in this direction. By doing that, we've added a new layer, and then eventually we have a flat terrace up at the top that we have to form a two-dimensional nucleus and go through the same process. But the key thing is, it's like building a nice brick wall. We're doing it in a nice, orderly fashion, row by row, layer by layer, and that's why crystal faces form the flat surfaces that they do. Let me show you this process actually taking place on the atomic scale. This is a movie taken with a slightly different technique called scanning tunneling microscopy. What you're looking at are individual atoms of silicon. Those are real atoms, pictures of atoms. And this is taken by vapor growth in a special chamber, and this is a layer of two layers of silicon atoms growing across the surface. This is the octahedral surface on a silicon crystal. You're actually seeing layer by layer growth taking place in real time here. That's not an animation. This is a true movie of the process. And you can see the kinks in the steps, all the topography we were just talking about. It's pretty amazing that we can take pictures like this today. All right. Now, as I'd mentioned, each time we add a layer, we have to overcome that barrier to two-dimensional nucleation, except Mother Nature has a nice way of getting around that. And that has to do with certain types of defects in crystals known as screw dislocations. If James is in the audience, I've heard him say that a few times recently. He's got some really interesting samples that might be related to this. A screw dislocation is I'm not going to get into the details of this, but it's a type of linear defect in the structure of a crystal. And when a screw dislocation emerges at the surface of a crystal, it creates a step. Remember, steps and the kinks along steps are where incorporation is going to take place dominantly. Well, here's a schematic of a crystal. The screw dislocation is this red dotted line here, and where it emerges, it creates a tapering step. And these do exist. Here's an AFM image of a barite surface. There's a step that terminates. There's a screw dislocation that extends into the crystal at that point. Okay? So the topography that we're showing schematically here actually occurs here. The fact that this step tapers like it does into the dislocation causes that step to be self-perpetuating. It never grows itself out like the two-dimensional nucleation and spread that we just looked at. And so this one, we never have to if it exists, we never have to overcome that energy barrier of two-dimensional nucleation. And so this can continue to grow at the lowest energy state, and that's the most favorable. So most of our crystals, if we look at them, and I'm going to show you how to do this, we're going to see that they're growing by a mechanism that's related to steps created by these screw dislocations. And it's our second mechanism of layer growth. I'm going to first show you this in a model. This is a representation of a diamond surface, and this model was created by John Jazak. Many of you know John. He's a physicist at Michigan Tech and a collector of black little ugly crystals of graphite. And his student, actually, he also collects big ugly crystals of graphite. And sorry, John. This is an animation of growth on in this case, not graphite, but on a diamond surface, an ugly form of carbon, not so ugly in this case. And what he has here, this is the octahedral surface, or a model of it, a step that's created by a dislocation. So the dislocation emerges here, and it would actually extend down into the crystal where this dotted line is. The animation is based on a technique called a Monte Carlo simulation. So what he's doing mathematically is he's taking atoms and he's bringing them down onto the surface, and he's calculating the likelihood of them staying on the surface or detaching. And again, this is going to be very, very dynamic. So if he was to make this model and show every atom attaching, it would be a mess. You couldn't see anything. So what you're going to see in the animation is only those atoms which stay on the surface long enough so that they eventually become incorporated, they become buried. And what I want you to see is how that attachment of those atoms is occurring. So here's our surface. You'll notice the carbon atoms are coming down. Every once in a while, you'll see one pop up on the terrace, but most of them on the terraces, they detach. So atoms are being added to this step. The step is migrating out in this direction. Now, because that step truncated and terminated at the dislocation, we're now forming a step in this orientation. And so it will start to migrate like this as atoms are added to it. At some critical length, we start to form a step on the backside here. And so atoms will start to be attached, and steps of that orientation will move in this direction. Now, our first step has grown to the edge. It's no longer growing anymore. This one is continuing to grow in this direction, and now we see growth on the backside here. Eventually, we're going to end up with a step in the exact same orientation as our first one, but now one layer higher, or actually 3 layers higher because it's a 3-layer step. So this growth process is continuous, and the surface will continue to spiral around and grow out normal to the surface. This is a mechanism called spiral growth. It's related to those dislocations, and it's another way that we can add layer by layer of atoms and end up with nice flat crystal faces. The next slide I'm going to show you is a real movie, again taken by atomic force microscopy, where you can see spiral growth taking place in the laboratory. The nice thing about the AFM is it can be done underwater. And so this is a calcite crystal surface growing in a solution, in a solution cell, and we're actually looking at the steps migrate out and the spiral growth process occurring. So every one of these spirals, you can see a bunch of them in here, terminate. That's where the dislocation is emerging, and you can see the layers spreading out as atoms are being added. At this scale, we can't see the atoms, but we can see the step migration. Again, you're seeing spiral growth on the atomic or the molecular level. All right. Once that crystal stops, the topography can be preserved. So the spirals that we just saw, if the crystal stopped growing, if our solution was no longer saturated, we would have a pattern, a microtopography left on the surface. And in this case, it would have a spiral morphology. And so when you see something like this, you know that that crystal grew, or that crystal face grew, by the spiral growth mechanism. That is a manifestation of that. Now, the next slide I'm going to show you is the exact same surface. In fact, it's the exact same spiral. After about a half an hour of additional growth of the calcite in this experiment, and what I want you to tell me, the first thing that you see, do you see a spiral or do you see a pyramid? You see a pyramid, right? But now look closely. The spiral's still there. In fact, that defect, this one here, that's right there. And as this process continues to occur, the spiral's there, but your eye starts to focus in on the larger scale feature, and this is what we call a growth hillock. These can actually become large enough that you can see them with the unaided eye. And so as I mentioned, start looking at your surfaces of your crystals in specular reflection, and you'll start to see all types of interesting patterns, including spirals and growth hillocks. And now you can understand what those are, and they're telling you how your crystals grew and why those faces are beautifully flat. Let's take a look at a few macroscopic examples. Now, this is a little bit different, and for those of you who understand the difference, we can talk about what's going on. I don't fully understand it myself. But here's a beautiful growth hillock, 4-sided growth hillock. These are very common on English fluorites. Of course, we have twins occurring here, and that will block the process, so something else must also be occurring. But this is a growth hillock on this crystal's about 2 centimeters across. You can see that with the unaided eye. In special examples, these are particularly uncommon. You can actually see spirals on a macroscopic level. This vanadinite crystal is about 1 centimeter across, and you can see the spiral pattern occurring there. Again, both of these have grown by the spiral growth mechanism and are flat because of this layer addition of atoms. Okay. So we've talked about why different crystal faces, say the rhombohedron or the scalendrahedron, might form in a given system. And now we've also looked at how flat crystal faces form. I mean, it's the common thing in minerals, but it's actually quite amazing that they do that. Let me back up here. If we do have a crystal bound by absolutely flat faces, such as this cuprite, which it has cube faces, dodecahedral faces, and octahedral faces. If all of the crystal faces on this particular crystal are equally developed in terms of their size, we're going to get an equant crystal, such as this one. However, another thing that can happen is, even if we have flat faces and we have the presence of these, if one face, or one combination of faces, grows much faster than the others, and there are reasons for that, both extrinsic and intrinsic, things like defects and also the flow of solutions in particular directions, we can form crystals that, instead of being equine in shape, are very elongate, such as the chalcotrichite variety of cuprite. So both of these are cuprites, probably the same forms or some of the forms that we see on here, but these are very elongate. So we can take one set of crystal forms and have a variety of different morphologies depending on the relative development of those faces. All right. This is a diagram, and it's going to take a minute to explain, but we've seen about half of it. And what it tells us, it's an observation that many researchers had seen, and this was summarized by Ichiro Sunagawa. This diagram is used quite often. What we have on this axis is the supersaturation. So this is for crystal growth in solution. And remember, that's the driving force for crystals. The more supersaturated we are, the more the solution wants to crystallize. On this axis, we have the growth rate, and then this diagram is broken up into different regimes in terms of what the interface looks like. In other words, what's the morphology of the crystal? Do we have flat crystal faces, or do we have rough crystal faces? At low supersaturations, down in this region here, we don't have enough driving force to overcome two-dimensional nucleation, and so our dominant growth mechanism is spiral growth. And this is where most crystals form. If we look at our surfaces, we'll see spiral growth, helix, things like that very commonly forming or observed on those surfaces. If we increase our supersaturation to a point that's represented by X, and X depends on the system. It's different for calcium carbonate and barium sulfate. So this all depends on which system we're looking at, and of course, all the conditions that I'd mentioned, temperature, pressure, et cetera. At some point, however, we become supersaturated enough that we can undergo two-dimensional nucleation, and it's going to dominantly grow by that mechanism, because that's favored now. However, we can still have both of these occurring at the same time. Both of these growth mechanisms that we've just looked at are going to give us nice flat crystal faces. As we continue to increase the supersaturation, we eventually get to some point where we turn into a rough interface. We no longer have flat crystal faces. We end up getting a morphology that's rough, things like dendritic forms or spherolytic forms or fractal forms. And right at the boundary of that, if conditions are right, we'll tend to form hoppered or skeletal crystals. So let's take a look at this first, and then these, and then we'll wrap it up. When we're right at the right supersaturation state, as I showed in that diagram, the addition of atoms, rather than being layer by layer, is taking place preferentially at the corners and at the edges of a crystal. And so those will grow out faster than the center of the crystal faces. And as this continues, what we'll end up with is the classical hoppered morphology that's shown in this diagram here. Now, everybody has seen these. There are many minerals that exhibit it, particularly native metals. However, probably the best examples aren't minerals in actuality. They're synthetic crystals. They're those bismuths that you can get at many rock shops or crystal stores. I still think they're fantastic. This is in my collection. It's a 10-centimeter hoppered bismuth crystal, but it shows the phenomenon so beautifully. Of course, it does occur in natural crystals, again, in native metals. This is a hoppered octahedral crystal of gold. You can see the octahedral face is highly depressed in these layers that are depressed in the center. It can occur in other minerals other than native metals. This is a pyromorphite. The lead apatites, pyromorphite, mimetite, and vanadinite commonly form hoppered crystals. You can see the hoppering on these pyromorphites from Phoenixville, Pennsylvania. All right. Now, if we continue to supersaturate, we're past the point of hopper crystal growth, we eventually move into the formation of dendrites. And I want to show you a movie of the formation of a dendritic ice crystal. So ice is a mineral. It forms naturally. It's a crystalline solid with a specific composition. We all know dendritic ice crystals. Does anybody know what we call them? Snowflakes, exactly. So I want to show you a picture of a snowflake growing, this one in the laboratory. And you can see those. What's interesting is this is not an aggregate of crystals, it's a single crystal. On the atomic scale, and crystallographically, this is a single crystal, but it doesn't look like it because it has a rough interface. The overall morphology is not flat surfaces, but these dendrites. Of course, these form in nature as well, and native metals commonly show them. This is a sample that I really love. This is an amazing piece, and I'll quickly describe the location. There's a recent shale fire occurrence in Ohio, in the state of Ohio, where a collapsed shale embankment spontaneously ignited because the pyrite was oxidizing. And anyway, you can read about it in Rocks and Minerals in the upcoming issue. But the minerals that were growing in this pile of shale are fumarolic. They're growing from gases that are being emitted from it. And this is a sample of sal ammoniac. It was photographed by Pete Richards, who's the first author on that paper. And it's, from a crystallographic point of view, and what we're talking about today, just fabulous, because you can see these crystals down in here. What morphology would we call these? Hoppered. But the hoppered crystals near the edge here are starting to grow out preferentially at the corners, forming these dendrites. So we're right on that boundary between hoppered growth and dendritic growth on the Sunagawa diagram. Of course, these can occur in other things like native metals. This is a silver specimen from Michigan, showing a dendritic habit, and a very large specimen of copper from Michigan. Interestingly, is just with the snowflake, very rough morphology, but from a crystallographic standpoint, this could be a single crystal, okay? Except it has a rough interface. So I'll wrap it up here, and I'll just finish by saying, if you're interested in following this, I know it gets kind of heavy sometimes, but there's a wonderful book if you want to start and learn more about crystal growth, written by Ichiro Sunagawa. This is the cover, Crystals, Growth, Morphology, and Perfection, and you'll notice that book grew by what mechanism? The spiral growth mechanism. All right, thank you very much.